Hello, my name is Santiago Pagani. I'm part of the research staff at the Chair for Embedded Systems in the Karlsruhe Institute of Technology, and today I'm going to present our work titled Thermal Safe Power, Efficient Power Budgeting for Heterogeneous Manycore Systems in Dark Silicon. A power budget is an abstraction from thermal issues. State-of-the-art power budgeting techniques are single or constant per chip or per core values, which present a neither thermally unsafe or pessimistic behavior. This can be observed in the following example, in which we have a 90 watt per chip budget and a critical temperature of 80 degrees. When we equally distribute this 90 watt per chip budget in 8 active cores, we observe that the maximum temperature in the chip is precisely the 80-degree critical temperature, which is the desired behavior. Nonetheless, when we equally distribute this 90 watt per chip budget in more than 8 active cores, we observe that the maximum temperature in the chip is below the 80-degree critical temperature, meaning that the active cores could be actually consuming more power, which translates to higher frequencies and higher performance. Contrarily, when we equally distribute this 90 watt in less than 8 active cores, what we observe is that the maximum temperature in the chip is above the critical temperature, meaning that some dynamic thermal management technique would be triggered, thus decreasing the temperature in the chip at the same time that the performance is also decreased, which is not a desired behavior. If we now plot the maximum temperature in the chip when we have different number of active cores with this 90 watt per chip budget, we clearly observe this thermally unsafe or pessimistic behavior depending on how many cores we have active in each case. If we now consider different per chip values as different budgets, what we observe is that this curve either goes up or down depending on the value of the per chip budget, having either more points that are thermally unsafe or more points in which we have a pessimistic behavior. A per core budget is not an exception, and although we have a different shape in the curve, we still present the similar behavior. The thermal safe power, or TSP, is a novel power budgeting concept in which the power budget depends on the number of active cores, such that we are both thermally safe and not pessimistic, which means that the maximum temperature in the chip is precisely the value of the critical temperature, no matter the number of active cores. This thermal safe power is derived by considering the worst-case mappings, which means that we have a power budget that depends on the number of active cores, and for any m active cores, this power budget that we have is going to be safe, such that we can abstract from mapping decisions. This basically can be seen with this example, in which we have a TSP value when we have 4 active cores of 14.67 watt, and we can see that for different mappings, the maximum temperature in the chip does not exceed the 80-degree threshold. If we now compute the TSP values for different number of active cores, we can observe the per core budget, which is this thermal safe power, which is not constant for the different number of active cores, and when we compute what the total per chip value would be of the power consumption, we observe that this is also not a constant value, which is different from the state-of-the-art per chip or per core power budgets. Our experimental evaluations conducted in both homogeneous and heterogeneous cores show that TSP actually results in higher performance than state-of-the-art techniques. Here are the results for homogeneous systems compared with different per chip and per core power budgets, in which we observe that TSP results in a 12% higher average performance when compared to all the constant power budgets. Thank you for your attention.